Okay, so for today's lesson, what we're going to do is we're going to talk about arithmetic sequences, kind of pick up from where we left off the other day, and we're going to learn how to write these arithmetic sequences using what's called the explicit and the recursive formulas. Fancy kind of vocab words, but don't worry about it, not so much of a big deal. So here's just kind of a review about what we talked about the other day. We had a list of numbers written out, and a sequence is just that ordered list of numbers that often form a pattern. We talked about terms of a sequence. Each number in the list is called a term. So the first number is the first term, the second number is the second term, etc. When you have an arithmetic sequence, it's a sequence in which the difference between consecutive terms is constant. It's the same value. So the other day we had numbers like 1, 3, 5, 7, 9. So that would have a common difference of 2 because from one number to the next, you were increasing by 2. And then the common difference, which we happen to actually don't use the letter D for, the common difference, that's what you're increasing by or what you're decreasing by. So then what ends up happening is each term in a sequence is identified by using subscript notation. Subscript is just like an exponent, but it's dropped. It's subscript, not raised. So the general form for subscript notation is A sub n, where n represents the term number. Okay, so is it the first term, the second term, etc. in the sequence, and A sub n represents the value of the nth term of the sequence. So if I wanted to talk about A sub 12, well then I'd have to find the 12th term in my sequence, and that would be the value. So example 1, for the sequence below, identify each term in the sequence by using subscript notation, then determine the value of A sub 9, and that's the term that we want to find. So 7 is the first term, or we would call it A sub 1. 11 is your second term, A sub 2. 15 is your third term, A sub 3. 19 is your fourth term, A sub 4. 23 is your fifth term, and 27 is your sixth term. So you could see, hopefully pretty easily, that as you go from term to term, each time I go to the next value, all I'm doing is increasing by 4. So it should be pretty easy to find the next 3 terms. I just want to get out to A sub 9, the value of the 9th term. Well, if I add 4 more to 27, then I'm going to get 31. And if I add 4 more to 31, I'm going to get 35. And if I add 4 more, I get 39. And I keep on going down till I end up wherever I want to end up. But I found out where I wanted to end up. This term right here is A sub 9. That's my 9th term out. So essentially, A sub 9, the 9th term, happens to be 39. So what ends up happening is if you think about going out to A sub n, right? If you think about going all the way out to the A sub n term, well, think about the number before and the number after it. If I'm dealing with A sub n, the number after A sub n would be A sub n plus 1. That's the number after A sub n. But what if I wanted the number before A sub n? I got to go to the left. I better subtract 1 from my n. So that would be A sub n minus 1. So just see if that makes sense to you, that if I ask for A sub n, 1 more than that would be A to the n plus 1 term, 1 less than that would be A to the n minus 1 term. Because what we want to do is be able to use the sequence in example 1 to write each term as a function of the term immediately prior to it. So essentially what that's saying is, okay, well, I'm going to use the numbers that we had here before, 7, 11, 15, 19, 23, etc. Okay? And I can say, all right, well, my first term, A sub 1, was 7. My second term, A sub 2, was my first term plus 4 more. My third term was my second term, 11, right? My second term was 7 plus 4, or 11. My third term is my second term, which was 11, plus 4 more. My fourth term is my third term 11 plus 4, which is 15, right? My third term was 11 plus 4, plus 4 more. I could keep on going on and on. Think about this one. So my fifth term would be my fourth term, which happens to be 19, plus my common difference, plus my 4 more. So basically what's happening is the next term of a sequence is the prior term added by the common difference. It's the previous term, the prior term, added by the common difference. And essentially what's just happened is you have just actually come up with what the recursive formula is. It's basically saying to get from one term to the next, all I need to do is to be able to take the term before it and add the common difference. So if we talk about a notation here, this recursive formula, it's a formula used to represent an arithmetic sequence that relates each term of the sequence after the first to the term before it. Okay, so it's after the first to the term before it. So if I want to figure out what a sub n is, then I need to know what the term before that was, a sub n minus 1, and then I'm going to add the common difference. Remember, we had said this before, that when you're dealing with a sub n, the term before it is a sub n minus 1. The term after it is a sub n plus 1. So we're trying to find the term before it and then add the common difference. So take a look. Write the recursive formula of the following sequence, 5 to 8 to 11 to 14. Well, hopefully you realize that the jump up each time is 3. So the common difference is 3. So if I use this recursive formula, then to find any term, a sub n, I need to know the term before that one, and then I'm going to add 3 to it. And that's all you need to do. This, believe it or not, is your recursive formula for that particular sequence. All right, well, let's suppose you're asked to find the 50th term in the sequence. What strategy would you use? And that's going to take a lot of work if you're trying to go from one number to the next to the next to the next with all the common differences. So let's see, the one that we're looking at is example 3, which was 5, 8, 11, 14, and so on. So essentially you say, okay, well, this is good. I know my first number. My first term happens to be 5. The common difference, don't forget we did this already, the common difference is to add by 3. So then my second number is going to be my first number plus one more term, which is the common difference. To get to my third number, well, I know the first. I need to get 2 more terms, which means 2 more common differences of 3. And then if I want to get to my fourth term, I've got my first already. I need to go out 3 more places or 3 more common terms. Hopefully you see a pattern here. Let's just try one more. To get to my fifth term, I use my first term, which is 5. I've got to go out 4 more terms by adding my common differences. Well, take a look at the common differences that we're adding in relation to the term number that we're in. Basically, I've got to add, in this case, I've got 1 3 here, which happens to be 1 less than my common term. So I've got 1 3 that I'm adding. I've got 2 3s I've got to add, which is 1 less than the term position. I've got 2 of those common terms. When I look for a sub 4, I had 3 of my common differences. 3 of those is 1 less than the term position. I had 3 of those common terms. Out for my fifth term, I had to add 4 of those common differences to my first term that I knew. So if I want to go out 50 places, if I want to go out to my 50th term, I can say, okay, well, I know my first number, not plus, equals. I know my first term is 5, and I need 49 more places, and I need 49 more of those common terms of 3. which means a to the 50th is my first number plus 49 threes, which is 147. So my a of the 50th term, or the number at the 50th spot, is going to be 152. So if you know the first number, it makes it really, and you know the common difference, it makes it really easy to figure out how far you have to go, because it's always going to be the common difference being one less than the term position that you're in. Let's see if we can put that into a formula. This formula is called the explicit formula, where you only need to know the first term and the common difference, because what happens then is you say, well, I can go out as far as I want to a sub n. As long as I know my first term and I know how many places I want to go, then I need n minus 1 of those times the common difference. If I want 50 terms, I've got my first term I know, and then 49 more of the common differences. Okay, so let's see if that kind of helps here. Write the explicit formula for the following sequence. What is a to the 20th? What is a sub 20, the 20th term? Well, I know that my first term of the sequence is 3, and I know that my common difference keeps increasing by 5. So I can say my explicit rule, a sub n, is going to be my first term plus one less of those in terms of common difference, one less of the term place I want to get to. So my 20th term is going to be the first term in my sequence, 3, plus 20 minus 1, or 19 more of those common differences, 19 of those 5s. So a sub 20 is 3 plus 19 times 5. A sub 20 equals 3 plus 114. So my 20th term of that whole sequence is 117. Okay, so make sure that you're okay with that. As long as you know the first number and you know your common difference, you can find any number in that sequence. Okay. So here's another example where they give you the arithmetic sequence. It's represented by the recursive formula a sub n equals a n minus 1 plus 12. The first term in the sequence is 19. Write the explicit. Remember, the explicit formula basically is just saying, all right, so a sub n equals a sub 1, the first term, plus n minus 1 times the common difference. Well, the common difference is right there. The first term is right there. So all you need to write is a sub n equals 19 plus n minus 1 times 12. That's it. Example 7. They tell you that the arithmetic sequence is represented by the explicit formula here. What's the recursive formula? So the recursive formula is a sub n equals a sub n minus 1 plus your common difference. So then I can say, all right, let's see, what do we have here? This must be the common difference. This must be here, my first term. Well, you don't actually need the first term to write this particular recursive formula. So that's kind of good. So that's sort of irrelevant right now. But we would write in terms of recursive formula, a sub n equals a n minus 1 plus 22. All right, one more example. A subway pass has a starting value of $100. After one ride, the value of the pass is $98.25. After 2 rides, the value is $96.50. Write an explicit formula to represent the value and the usage, to represent the value and usage of the subway pass. What is the value after 15 rides? Well, let's think about this. We've got rides, we've got value. After one ride, the value on the pass was $98.25. $25. After 2 rides, the value ended up being for $96.50. Well, what is the common difference? If I think about this and I subtract those two values, I keep decreasing by $1.75. So that's your common difference. If I want to think about some sort of rule here, especially I'm looking for the explicit formula, I can say, well, I know what my starting value is. My starting value is my one ride. So I'm looking for this particular formula. A sub n, and remember, we're looking for the explicit. So A sub n equals A sub 1 plus n minus 1 times d. And then we're good because we know that we're dealing with what happens on the value of the card after 15 rides. So A sub 15 equals A sub 1, $98.25, plus n minus 1, 15 rides minus one more, right, times the common difference, negative 1.75. So I'm saying A sub 15 equals 98.25 plus 14 more rides where I'm losing that value of 175. Bring this down. A sub 15 equals 98.25. Now it becomes minus because 14 times negative 1.75 means I'm being charged that $24.50. So after 15 rides, my card has now $73.75 on it. One of the interesting questions to ask is why is $100 not the value after one ride? And that's something worth considering. That would be is my cards, if I don't have any rides at all, that's when my value is $100. It's not until after one ride, and that's what we're looking for. What is the money going to be left on the card after 15 rides? So that one ride is the $98.25 left. All right, so that's it. So hopefully you should be good on the homework.